Okay. Normally at the beginning of the class, I see myself in the big window. Right now, I see the Supercharged Science logo there. I need to see myself big so that I can tell whether I'm going off my rectangle. So I don't know if students are there yet. Okay, good. Okay, so I am live. I am going to start talking. I can't see myself very well yet, but I know it's going to happen soon. Welcome to Supercharged Math with Doug. I'm Doug. I think you should know that by now, but just in case there are any new people in the room, or new people in the Zoom, as it were. It is October. It is cold. I'm wearing slippers. I am talking about non-math topics because I like to do that at the beginning, just in case some of the students have not arrived yet, so that people don't miss the beginning of the class. My beautiful assistant Mocha is upstairs. She is not with me today, but she is still as cute as ever, I will assure you. And today's shirt is the Blues. I have to see there. It is the Blues, which is a rugby team from Auckland, New Zealand. And rather lovely shirt, I think. It has some Aboriginal inspired art, sort of a subtle art behind the logos. And with that, I think I can start talking about the math, and I will do that now. Okay, so we are talking about algebra, of course, and I have this label absolute value because the first thing I want to talk about is absolute value. And what is absolute value after all? Well, absolute value is when we force any number, whether it's positive or negative, to be positive. And there are reasons that we need to do that in math. The way we show it is with these two lines, vertical bars, which will have a number inside them. So the way we read this is, I am looking at the absolute value of 5. The bars tell me absolute value. The absolute value of 5, though, is 5, because 5 is already positive. So the absolute value of bars force it to be positive, but it already was. So we have the absolute value of 5 is equal to 5. That sounds like we wouldn't have to do it. But the reason we need to do it is because sometimes the number inside the absolute value bars is negative. And the absolute value of -5 is 5. Now, what's a situation where we would do this? I will erase and I will do a little bit of drawing to see if I can come up with a situation where this makes sense. So I will start with this erasing. And what I need is my yardstick. So I'm going to grab my yardstick, which is right here. Where is it? It was right here. There it is. Okay, so here's my yardstick. I don't want a meter stick. I want a yardstick for this because I'm going to draw a number line. But I choose to make my number line nice and big so that you can see it. So this is 3 feet long. It is a yardstick. Doesn't look very straight in the video, but it does look straight to me. So I'm just going to have to go with that. Okay, so I'm drawing a line that is 3 feet long, and I'm going to put little notches at 12 inches and 24 inches. And at the end, because I want it a little longer than that, so I'm going to add one more foot. There's 24, line up the line, there. Now, why am I doing this? I want to have a number line where I can show 0, and I'm going to put 1 here. So this number line is really stretched out. It would be useful if we wanted to show a lot of small fractions and decimals, but it's not really the reason I'm doing it today. Over here, we'll have -1, and that's supposed to be -1. It's a little messy, so I'll make it less messy, and -2. Okay, so what if I wanted to ask you, we all know how I did this. We all know that these two numbers are 1 foot apart. What if I were to ask you, how far is it from 0 to 2? Well, that's going to be 2 feet, of course, and it's obvious. But what if I asked you, how far is it between the 0 and the -2? Well, because we drew a number line, we could be tempted to say, oh, that's going to be -2 feet. But of course, -2 feet, a negative distance, does that make sense? Really, this is where it's useful to use the absolute value symbol. because this was 2 feet and the absolute value of 2 is 2. And this is -2, but the absolute value of -2 is 2. This was also 2 feet. I was just counting it in the other direction. So that's an example of when we can use the absolute value symbols to give us answers that make sense. When I want to know how far it is between here and here, I don't want -2 feet as the answer. I want 2 feet as the answer, and I can just make that happen by using my absolute value symbols in a clever way. I'll put down the yardstick now because I don't think I need it anymore, and I'm going to look at my notes to see what was the next thing. Oh, yes, I want to talk a little bit about inequalities. Well, a little bit. I want to talk a lot about inequalities because that's really the focus of this week's lesson. So I will erase my cute little number line, and we will talk about inequalities. I am also keeping an eye on the chat. If you are able to type into the chat, then students definitely can type answers to questions that I am asking into the chat or suggestions for questions. Sometimes I'm able to take those. I really like to get the students involved in the lesson. So if there's something there, I'll see if I can use it. I will check every now and then. And this piece of chalk is too short, so I am going to put a brand new one into my chalk holder. There we go. Inequalities. I won't write the word inequalities. Okay, inequalities. What are those? Those are the things in math where we use the less than, the greater than symbol, the less than or equal to symbol, the greater than or equal to symbol. Okay, what's a real life situation where we have to deal with this? The example I came up with was, how about to get a free item when you're ordering food from a restaurant, you have to spend at least $20. At least $20. Phrases like at least and at most and no more than in math very often indicate to us that we're going to need one of these symbols. So at least $20. How am I going to show that? I'm going to show that with greater than or equal to $20. I won't put the $ unit. So greater than or equal to 20. This means at least 20. So what would happen if you spent less than $20, this less than symbol, you would not get the free item. What would happen if you spent greater than $20? You would get the free item. And then, of course, you have to be careful. What if you spent exactly $20? Well, this is not greater than 20. This is greater than or equal to 20. So being greater than 20 gets you an item, but being exactly equal to 20 also gets you an item. And there we have it, a real life situation, which could be presented to a student within a word problem, perhaps, where it would make sense to use one of these symbols instead of just using an equal sign. So with inequalities, if we use the equal sign, we can often figure out the answer. So if I spend $23, I might say, okay, $23 is not equal to 20, but I can still figure out that it's more, so I know I'm going to get my free item. But using one of these symbols can make it more convenient. That's the way I like to show that. Now, and I finished the first page of my notes, so I'm going to take that page off of my clipboard and get it out of the way. And while I do that, I will remind you that students who have questions can send me questions by email at doug@superchargedscience.com. Okay, so when we start dealing with the inequalities, the first thing I want students to be able to do is to graph inequalities on the number line. So that's what we're going to do next, and we're going to do quite a few examples of it. How about graphing x greater than 4 on the number line? I'm not going to use a ruler to draw my number lines because it would take too much time, so I'm going to do my best to draw a decent number line. When I draw a number line, I like to show 0. In nearly every problem, some problems involve numbers that are very far away from 0, and you don't always have to show 0 on your number line, but I like to show 0. And if I have very large numbers or numbers that are very small in the negative direction, I prefer to show the 0 and just change how I scale the number line instead of trying to show a number line with no 0 on it. 0 is an important number in a number line. So I'm making sure to show 0, but I also have to show 4. because 4 is involved this time. So I want to show 4. I'll put 4 here. Now I have an idea of how I want to scale this. I'll put 2 halfway between 0 and 4. Anyone surprised? And then I put my 1 and my 3. And I also really like to show numbers on both sides of the number I'm dealing with. So I make it long enough so I can show at least 5 and maybe 6. And then I also want to show the negative numbers. So the negative numbers, using the same scale, -1, -2, -3, -4, -5. I can even fit -6. Over here, I have a number line I am able to graph now. How do I graph the numbers that are greater than 4? Now that I have the number line scaled the way I need, I know that 4 is a very important number in this inequality. I'm going to put a circle on 4. And I like to use a nice big circle, because whether that circle is filled in or not is meaningful when we deal with inequalities. The numbers that are greater than 4 are over here to the right of that circle. So I'm going to shade those. And I'm using shading because I know that even weird decimal and fraction numbers like 4.5 or 4.9 or 4.001, these are all numbers that are greater than 4. So they have to be shown with shading. All the numbers over here, whether they're convenient whole numbers or not, that are greater than 4 are part of my answer. And because it keeps on going after 6, I'm going to put a ... to show that it keeps on going. The last thing to consider is, should I fill in this 4? No, because 4 is not greater than 4. 4 is equal to 4. And this symbol is not greater than or equal to. So when it's greater than or equal to, I will fill in the circle. But when it's just greater than, I won't. Okay, so this is not very hard. I'm sure most of the Supercharged students do not find this hard. But should we do a few more? Yes, because there are so many things that can happen. It looks like this is so simple. Every other example would be just the same as this. Not really. Remember, we have 4 different symbols. We have greater than and less than. And they do different things. We have greater than or equal to, less than or equal to. So the or equal to does different things. And then we have positive numbers like 4, but also negative numbers. And that causes different things to happen. The negative numbers are over here on the number line. So we need to do quite a few examples so that we can make sure that we've seen everything and nothing can surprise us anymore. I will do a few more right now. And I'm also going to check with values sometimes. So how about if we check the number 5? Is 5 greater than 4? Yes, it is. So therefore, 5 should be shaded, and it is. How about if we try -3? Is -3 greater than 4? No, it's not. So -3 should not be shaded. So we're able to check with numbers to make sure that the graph, which is what this is, makes sense. Now I will erase, and I'll do a few more examples, and I will occasionally check them with numbers. How about x less than -3? Okay, so the same strategies apply for building my graph. I draw the line. I make sure to put 0 on it. I make sure to put -3 on it, which will be over here. So I don't want to put -3 right at the end of my line. I want to put it comfortably within so that there's room for at least one more number. Using proportional scaling, -2 will logically be here, -1 will be here, -4 will be here. I can't really fit any others, but I have numbers on either side of -3, so I'm able to see what I'm doing. And then I want my positive numbers as well. And those ones fit, and that's enough. Now, less than -3, well, I have to show -3. I need a dot on -3. I'm putting a nice big dot. Will I fill it in? No, because it's not less than or equal to -3. It's less than -3. And now be careful, because it could be tempted when looking for numbers that are less than -3 to think -2 must be less than -3. But no, the numbers that are less than -3 are over here. So we're shading on this side. And we put ... to show that it keeps going. I have graphed x less than -3. How about plugging in a number like 1? Is 1 less than -3? No, 1 is positive. 1's greater than -3, so 1 is not in the shaded region. How about a number that doesn't even fit on here, -10? Is -10 less than -3? Yes, but -10 is shaded, because even though I didn't show it, the ... shows me that -10 would be shaded. So I have a graph of x less than -3. A bit more variety. Let's do a different one. X greater than or equal to -2. Okay, not too different, but wait, no. The last one we had a less than. This is a greater than. The last time we had less than. This one we have a greater than or equal to. We have the or equal to happening. But we do have a negative number like we did last time. So I show 0. I want to show -2. That means I'll show -1. I want to show -3. I'll make the number a little longer. And then I can show 1 and 2 and 3 and label those. The number I'm dealing with is -2. This is starting to be faster and easier to do, I hope. The number I'm dealing with is -2, so I put a circle on it, but it's or equal to. So I'm going to shade in that circle on -2. Greater than. Be careful, we did that side last time, but this time it's greater than. The numbers greater than -2 are over here. So I have to do all this shading all the way over here, all the way to the end, and then put the ... so that we see it keeps on going. We have an answer. 2 is greater than or equal to -2, so it should be shaded, and it is. -3 is not greater than or equal to -2, so it should not be shaded, and it isn't. We do the numbers to check, and we see that it all makes sense. Few more. We haven't really tried all the different things that can happen. How many different things can happen? How many different number lines can I do where I'm using different strategies or having different things happen in the answer? Well, there are two to choose from between less than and greater than. There are 2 to choose from between or equal to or not having or equal to. And there are 2 to choose from between positive and negative. So does that mean there are 6 things that can happen? No, it means there are 8 things that can happen. So try and figure that out because I'm multiplying 2 times 2 times 2. Okay, so the next one I have is x less than or equal to 1. I'm showing my number line, I'm putting my 0, I'm showing 1, I show at least one number on either side of 1. I show some negative numbers as well. Less than or equal to 1 will be over here, but wait, I'm going too fast. The 1 is important. I need a circle on the 1. Less than, and now what do I do next? Do I worry about whether I fill in the circle next, or do I do the shading next? That doesn't matter. That is a matter of preference. So less than or equal to, well, the numbers less than 1 are over here, so I have a whole bunch of shading to do, and I need a ... and then it's or equal to, so I have to shade in the circle as well. It's graphed. So we have done now 3. We have done 4 of the different things I can think of happening, and I'm going to do all 4 of the others. How about x greater than -5? Okay, the numbers are starting to get a little larger. I can't keep using 1s and 2s all the time. So I have to be able to handle it when the numbers are larger, but that's not hard. I draw my number line. This time I didn't even draw the number line as large. It doesn't have to be a very large number line. I put my 0. I show -5. So to make -5 fit, I ended up putting it a little closer to 0 than I did in previous ones, but that's okay because I just make sure that I scale my whole number line that way. -1, -2, -3, -4. Here's -6. I'll show 1, 2, 3, 4, 5, 6, and even 7. So it ended up being a little crowded. If I don't want it to be so crowded, well, I can make the line longer, and then I can still fit all of the numbers I need. -5 is where I need a circle. It does not say or equal to, so I'm not going to be shading in the circle. The numbers greater than -5 are over this way. So I have quite a lot of shading to do, get all the way to the end of this number line, and I put my ... I did it. Let's do another one. This is important. It does seem easy, but it's important. And it's good for students to take their time and do a lot of examples so that they really are firm in their knowledge of how this works. X less than 6. Again, the numbers are getting a little larger. One of the things I could do to make the numbers fit easily and to not have so much clutter is I don't have to scale up and down by 1s. I can scale up and down by something else if I want, like, for instance, 2s. So I'm showing 2, 4, 6. I think I want to show 8. I'm showing -2, -4, -6. I have enough. The 6 is the important number. So I have to make sure, even though I went up by even numbers, if I had a 7 there, that would be a little awkward. It would be hard to show. So I would want to make sure the number that I'm actually dealing with in my inequality is one of the numbers that show in my scaling. Less than 6 means I am shading in this direction, so I have a lot of shading to do. And I put the ... to show it keeps going. Do I fill in the circle on the 6? No, because it is not less than or equal to, it is less than. Okay, is there anything else I can do to make this have more variety so that the students are entertained? Well, I can try to think, what is it that I can do now that I understand this so well? What is it I can do that might add an extra bit of a challenge? How about this one? 0, can we use 0? Yes, we can use 0. We draw our number line, we make sure to show 0. We have to show numbers on either side of 0. I'm choosing to do this. That's a 1, -1 and 1. Okay, I didn't even bother showing 2 or -2 because I don't really have to, because 0 is the key number that I'm putting a circle on. It's or equal to, so I have to shade it in. It's greater than, and that's going to be over here, so I'm shading over here. And I put my ... The fact that it was 0 didn't really present any new challenges. We can deal with 0 the way we deal with the other numbers. One last example. Can we do this with very large numbers? I think we know that we can. I'm just double checking the chat. Okay, how about x less than or equal to -70? Okay, I have to do some clever scaling now. I still like showing my 0. So I'm going to draw a number line. I'm going to put my 0. I like my 0 to be in the middle. But again, you don't have to, but I choose to. To fit -70, though, that means I am going to have to scale in a clever way. So this is -10, -20, -30, -40, -50, -60. Finally, I get to -70. I'm going to make it longer, though, because I want to make sure to show -80 so that I show numbers on either side of -70. That's hard to read. It's small. It's cluttered. I can deal with this by making it bigger. And I'll show 10, 20, 30, 40, 50, 60. And quickly scale them. I see I'm using the less than side. So a lot of this number line I'm not going to need. But -70 is my key number. I'm putting a circle on it. It's or equal to, so I'm shading that in. It's less than, which is in this direction, so I'm shading over here. And I'm putting my ... I was still able to do it. I walked off camera, but my answer didn't. I was still able to do it. I was still able to fit the answer. And finally, I have done all of the different styles of example I can think of about this. So it's time to do something new. Another topic within this week's algebra topic. What if we have a statement like this? So now we're putting the two ideas together, the idea of absolute value and the idea of graphing on the number line with the less than and greater than signs. Absolute value of x is greater than 2. How am I going to show this? I'm going to draw a number line. It really does look crooked on the chalkboard wall. I think my camera is a little bit tilted. Let me just try see if I can fix that. No, I went in the opposite direction to what I wanted. How about if I tilt the laptop that has the camera on? Nothing I do is working, never mind. Okay, you'll just have to trust me that to me, this is a straight line that's not tilted very much. Maybe a little bit, but really looks tilty in that video. Okay, I need to show 2. So I'm going to put a 0. I'm going to scale it in a way that shows 2 and shows some numbers on either side of 2. But because of the absolute value, I think I need to show -2 as well. So my strategy of always showing this number is going to be expanded to show that number and the negative version of that number. So here's -1, -2, -3, -4. Now I can show the 2 and the -2. I think I need to try plugging some numbers into this and simplifying it to see if I'm getting an answer. Remember how we were checking our number lines before by plugging numbers into the inequality? Well, we can make our number line, figure out where to put things by plugging numbers into the inequality. So how about if I put -3, x equals -3. If I plug that into the inequality, I get the absolute value of -3 greater than 2. The absolute value of -3 is 3. So now this says 3 is greater than 2, and that's true. So 3, because it's giving me a true statement, is going to be part of the answer. It's going to be part of the area that's shaded. I'm going to put a circle on my 2, and I realize that 3 is going to be part of my answer. So that tells me I'm shading over here. Okay, let's make sure though. I'm going to try, oops, -3. I'm getting ahead of myself. I was saying I needed to show my 2 on the number line. I have to show my -2 as well. And that's why, because I didn't start with 3. I started with -3. So -3 is giving me a true statement because the absolute value of -3 is greater than 2. It works. Therefore, I'm going to be shading over here. So I feel like I'm going to be doing this shading, but I'm going to double check. I'm going to do another number, which is -4. I may as well try -4. So where will I do this? I'll do it down here. The absolute value of -4 is that greater than 2? The absolute value of -4 is +4, and +4 is greater than 2. It is true. I'll just put a T for true. That means -4 should be shaded. And this is making sense. I'm shading over here. But then I'm saying to myself, wait, what about these other regions? I need to plug in some of the numbers from here in the middle and from over there just to make sure that I'm finished with my graph, because I really have a feeling I need this. Well, I know I need this. So how about plugging in 3? If I plug that into here, the absolute value of 3 greater than 2, of course, the absolute value of 3 is 3, and 3 is greater than 2. That is true. So this is also going to be shaded, and that makes me realize I'm going to need to shade over here as well. How about 4? I'm going to do it without writing it down this time. The absolute value of 4 greater than 2. The absolute value of 4 is 4. Is 4 greater than 2? Yes. So the fact that I shaded over including the 4 makes sense. Shading this way is going to be correct for the answer. And of course, numbers larger than 4 are also going to work. The absolute value of 5 is going to be greater than 2. The absolute value of 6 is going to be greater than 2. So I need my ... Do I need another ... over here? I didn't really leave much room for it. But how about -5, which would be off the graph a little bit over here? The absolute value of -5 would be +5. And +5 is greater than 2. So yes, I need a ... over here as well. Do I shade inside these two circles? No, because it's greater than. It's not greater than or equal to. So that little skill and bit of knowledge that we already had developed still applies. I am finished. I have managed to successfully graph this. But wait, is Doug completely sure? What about -1, 0, and 1? What happens with those? Well, I'll try one of them. I'll try -1. If I put -1 in here, I have the absolute value of -1 greater than 2. The absolute value of -1 is +1, and the +1 is not greater than 2. That is a false. So that -1 should not be shaded, and it isn't shaded. This is interesting. And we start seeing patterns emerge that will make it easier and easier. I really went to a lot of trouble to show all the details this time because we're just starting with this. But we start seeing some things that are useful. When we're doing this, seeing the number and putting a circle on it right away, but also putting a circle on the negative version of that number is going to be a useful thing to do. Let's do another one, though, and make sure that we have seen all the different things that can happen. My next one, I used a greater, so I want to use a less than. I used one that didn't have the or equal to, so now I want to use one that does have the or equal to. So let's try that. Lots of erasing. And remember, when the teacher's erasing and writing down new problems, that's the time for the student to get a sip of water or stretch or get up out of their seat and just stretch their legs a little bit. I need the stretch. I find that this sort of work makes my shoulders become tight, and this kind of stretch feels really good. Is it because my shoulders are close to my brain and I'm thinking a lot? I think so, but I need that sip of water as well. Okay, next one. Absolute value of x less than or equal to 3. Okay, well, I need a number line, so I'll draw one. I won't worry too much about how crooked it looks in the video. I'll show my 0. I have to show 3. So 1, 2, 3. There's 3. I'll show 4 and 5. And I want to show -1, -2. For sure, I know I want to show -3. And I show -4, and that's going to be enough. I won't make the line any longer. And the 3 is involved, so I'm going to put a circle on it. But I think the -3 is also involved, so I'm going to put a circle on it. Now, I want to be careful and try some numbers. Let's try 4. The absolute value of 4, is it less than or equal to 3? The absolute value of 4 is 4. And is 4 less than or equal to 3? No. So that means 4 is not going to be shaded. And I'm not too surprised, because shading on the outside of my number happened last time. But the last time I had a greater than symbol, and this time it's a less than symbol. Let's try 2, because I have a feeling it's going to need to be shaded. The absolute value of 2, is it less than or equal to 3? The absolute value of 2, of course, is 2. And 2 is less than or equal to 3. It is true, so I'm going to be shading. I will be shading in here. Am I sure? Do I want to shade all the way over to this other dot? I feel confident, but I'm going to check. How about -1? The absolute value of -1, is it less than or equal to 3? The absolute value of -1 is +1. Is +1 less than or equal to 3? Yes, it is true. I need to put a T here as well. Okay, so therefore, -1 is also part of my shaded region. It's part of my answer. So I do feel safe now to continue my shading. But once I get to that other dot, I'm going to stop and be careful and see, what about -4? Would I keep going? With earlier examples without the absolute value, I would have kept going. But this is different. We have absolute value now. -4. The absolute value of -4 is +4. Is +4 less than or equal to 3? No. +4 is greater than 3. So that is a false. Therefore, I do not want to shade this. And now I feel confident that I'm finished. Since I didn't go off either end of the number line, I don't need a ... And what else is there to do? Is there anything else to do? The students can type things into the chat if they think I forgot anything. But I know supercharged students are probably thinking several steps ahead of me, because that happens a lot with this type of student. And I like that. Keeps me on my toes. Yes, I have forgotten something. And yes, of course, students are saying right now they're typing away, or they're running closer to their keyboard or something. They're worrying about whether they should capitalize the words, but they're trying to express themselves, and they're saying, you forgot the or equal to. These circles have to be filled in, and those students are right. So because it is or equal to, I am going to fill in the 3 and the -3. But I want to test that too. So let's try the -3. Plugging negative numbers into absolute value seems to be more fun, because more stuff happens. If we plug -3 in here to see if it is less than or equal to 3, the absolute value of -3 is 3. And 3 is not less than 3, but it is equal to 3. So yes, I should be including -3, and that's why I have to fill in that circle. If I plug in +3 into my statement, something very similar is going to happen. So what's the pattern? The students have to be noticing a pattern. So I don't know, should I say it? I don't want to say it. What I'll do is I'll hint at it. Okay. Sometimes we find our numbers and we put our dots, and then we shade outside of both of them. Other times we find our numbers, we put our dots, but we shade in between them. And there's a pattern that is dictating whether we do this or not. And the pattern will be obvious when we do a couple more examples. So I have 2 more examples of this, and I'm going to check my time. Let's see where I was at and how much time I was expecting to spend on each thing. I think I'm doing pretty good for time. I will stop for a moment to take a sip of my fizzy water. Okay, now this fizzy water is supposedly ginger ale flavored. Okay, it's not ginger ale. It's just a little hint of ginger ale, and I like that. Okay, I'm going to do some erasing. And then I'm going to do another example. I will go a little faster. I will plug less numbers in because we're starting to feel comfortable with this. So we can start sort of talking our way into knowing where to put the shading instead of having to prove it all the time by plugging in numbers. How about the absolute value of x is greater than or equal to 5? Okay, I can graph that. I want to make sure to show a 0. I want to make sure 5 shows on my number line. But I want to make sure some numbers on either side show. So that makes me say I'll put 2 here. There's 1, there's 3. This is pretty good. And I'm able to fit 6. But I'm also going to show -1, -2, -3, -4. These are crowded a little too close together. I'm not doing it very well. I'll even erase a little bit. Okay. And now, oh boy, it is crowded. When on the side with the negative signs, it is more crowded. But I'm definitely going to show the -5. And I can fit everything. It is a little cluttered, but I can fit everything. And I think it can be seen fairly well in my beautiful crooked no ruler number line. Okay, so we know that we have to circle our 5. And we'll circle our -5. These are things that we're not talking about as much because we're starting to feel comfortable with them as being part of the process. And then we can start thinking our way through whether certain regions should be shaded. That pattern we were talking about, the greater than, that was the one where we shaded on the outsides of the 2 numbers we put circles on, wasn't it? So let's try that. How about -6, which is on the outside? The absolute value of -6 is going to be +6. And +6 is greater than 5. So that's true. I am going to shade the outside here. And I'm going to put a ... So I'm starting to feel confident. -7 will also work. How about, whoa, something I hadn't really done yet, but what about all those fractions and decimals between the whole numbers? What about -5.5? If we make that the absolute value of -5.5 and test whether it is greater than 5, well, the absolute value of -5.5 is going to be +5.5. And it is greater than 5. It's working. It's true. So that shows proof that I do need to shade in this little area here just to the left of that circle. And then we look for the or equal to. There's an or equal to, so I'm going to have to shade the circle itself, which means I'm going to shade this one. Let's think about 6. Is 6, the absolute value of 6, greater than or equal to 5? Yes. The absolute value of 6 is 6, which is greater than 5. I'll be shading on the outside. The pattern we're noticing is true. When you have greater than or equal to symbols, you will find yourself shading the 2 outside edges and needing the ... on both sides. And not shading in between, but we want to check that as well. How about we try -2? Absolute value of -2 greater than or equal to 5. The absolute value of -2 is 2. Is that greater than or equal to 5? No, it is not. It is false. So therefore, we will not shade -2. We have our answer. And the pattern, of course, is greater than, shade outside the numbers. Less than, shade between the numbers. We'll do one more example just to test that a bit. Greater than or equal to, just like the earlier examples. We shade inside of our circle, our circles. So this is pretty fun. And it's good to practice a lot with these basic little questions, because as you stretch your mind with bigger and bigger concepts, you'll have this to fall back on. And it'll make you be on steady ground as you build those bigger concepts. How about absolute value of x less than 1? Let's apply the patterns and try to do this one quickly. Draw the line, put a 0. It's only 1 that I need, so I'll put nice big spaces between my numbers. 1 and 2 both fit. -1, -2. I see that 1 is involved, so I want to circle there. And therefore, I want to circle on -1. The pattern was when it's less than, I'm shading in between. So I test that quickly. 0 is in between. The absolute value of 0 is 0. Is the absolute value of 0, is 0 less than 1? Yes, it is. So I feel safe to shade in between. I don't need dots. It's not or equal to. I don't need to shade inside the circles. That actually was really fast, wasn't it? So you find your number, you put circles on both that number and the opposite signed version of that number. And if it's less than, you're going to shade in between them. If it's greater than, you're going to shade on the outsides of them. If it's greater than, you will be putting dots on both sides. If it's less than, you don't need any dots. If it's or equal to, you shade inside the circles, but we already knew that. If it's not or equal to, then you don't shade inside the circles. That was really fast, so much faster than the first one. And that's the end of my second page of notes. So let's get this off of my clipboard. And I want to compare. Now we're going to start doing some algebra that involves these symbols. We have been doing a lot of practice of algebra that had equal signs. The symbol is instead of the equal sign. So we have to start doing some algebra that has that symbol, well, one of those 4 extra symbols instead of the equal sign, and see how it feels. What I'm going to do to start with this, though, is I'm going to do a 2-step algebra problem like we were doing last time. But I'm going to do it with an equal sign, and then I'm going to do the same problem with less than or equal to. Oh, that's interesting. The point is that the rules of algebra that we've learned that involve moving things away from our x so we can isolate our x, applying all those rules, we can still do these when all these rules when we have the new symbols, the less than, greater than, less than or equal to, greater than or equal to. The algebra techniques still work, but we'll prove it by doing it twice. So what do we do here? We're adding a 1 to the term that includes x, so we do the opposite, we subtract a 1. But if we're subtracting a 1 here, we have to subtract a 1 on the other side as well. These cancel. Notice how fast I'm going because we did this so much of this last time. I know the students are good at it now. 2x is now isolated, but my x isn't isolated. 9 minus 1 is 8. To get rid of this 2, my x is being multiplied by a 2, so I divide both sides by a 2. These cancel. X is equal to 4. I have my answer. Here, I am adding a 1. I do the opposite. I subtract a 1. From both sides, these cancel. 2x is less than or equal to 8. I am dividing both sides by a 2 to cancel out the fact that x is being multiplied by a 2. These cancel. X is less than or equal to 4. I have my answer. And of course, I would be able to graph this answer on a number line because that's one of the ones that we did a few minutes ago. So if we wanted to, we could do this question and graph it on a number line. Let's do it very quickly. Okay, I'll show my 0. I'll show 4. I'm not going to show all the numbers. I won't label all of the numbers. Less than or equal to 4, I need a circle on the 4. The or equal to needs to be shaded. Less than is on this side. There's no absolute value in this one. It keeps going and there's a dot, dot, dot. Okay, how about graphing this on the number line? I need more chalk. Need to show my 0, need to show my 4. I'll put a circle on the 4. X equals 4. That's not or equal to, but it's equal to. We need to shade this. But there's no less than. So I don't need to shade to the left or to the right of it. This is graph now. Putting one dot, shaded in dot, on the 4 is the appropriate graph for this answer because x equals 4. Well, this is all there is to it. So maybe you think that graphing one of these on the number line is a little boring, but certainly this isn't. There's more to this. So that's cool. Let's do a slightly larger algebra problem, a 2-step algebra problem, but with the greater than, less than symbols, and let's practice this a little bit. Now, how much is new here? We already knew how to do the rules of algebra. So the only thing that's new is now we have the greater than, less than symbols, and we don't have to show all of our answers on our number lines. So there's not really very much that's new. Let's try. Let me think here. I'm also watching the time because there are certain things I want to make sure I have time to include. I think I can get into this example. 10 minus 2x greater than 20. Yeah, I want to do this. Okay, so is there anything else that's new? That's what I'm after. There is something else that's new. We know all these rules of algebra, all this moving things across the equal sign when it's adding and subtracting, how you do that. When it's multiplying and dividing, how you do that, and how the multiplying and dividing is slightly different than the adding and subtracting. What you do on one side of the equals, you have to do on the other. If it's an inequality symbol, what you do on one side of the inequality, you have to do on the other. All of these rules of algebra that we've been practicing so much the past few weeks will still apply. So there's one more new little detail that happens because of these symbols. And that's why I want to do this example, and I need to slow down. Okay, what's happening here is my x is being multiplied by this 2 or this -2, depending on how you want to see it. But it also is having this 10 added to it. I know the 10 is being added because it's not a -10. So what's the opposite of addition is subtraction. We are going to subtract a 10. But we have to do that on both sides. So far, nothing new. The 10 minus 10 cancels. We can't lose this sign. We still have -2x. We don't have 2x. 20 minus 10 is equal to 10. Okay, now my x is being multiplied by a -2. I have to divide both sides by -2. These cancel. My x is isolated. 10 divided by -2 is -5. And here's where we have a new rule. This symbol has to flip backwards. It's greater than, it becomes less than. Why? Because it's a rule that you have to know, which is when you divide both sides of an inequality by a negative number, the symbol has to flip. Once you know that and remember to do it, everything's okay. But really? You have to do that? Well, let's test it. X less than -5. We know what that means. We know that, for instance, -10 is less than -5. So if I plug -10 into this inequality, it should give me a true answer. Notice, I'm not talking about -10 greater than -5. No, this statement where we have x isolated is less than. So -10 is less than -5. It should give us a true answer. Let's try plugging it in. 10 minus 2 times -10. So all I'm doing is taking my x and replacing it with this value I want to test. Is greater than 20. Negative times negative is positive. So -2 times -10 gives me +20. And 10 plus 20 is 30. And 30 is greater than 20. So it worked. Using my original inequality, using -10 that I know has to be part of my answer because it is to the left of -5 on the number line, it worked. But if I had tried to use, if I had not turned the symbol around, I wouldn't have realized that -10 was one of the right answers. So something interesting has happened there. And it's not, it might seem confusing, but it's not confusing so long as you remember the rule. When you divide both sides of an inequality by a negative number, you have to flip the symbol. And we'll get used to that. But I'm going to do another one right away. First, I'll take a sip of this. Okay. Because it is the only division where you do this. No. A better way of saying rule is whenever you divide both sides of an inequality or multiply both sides of an inequality by a negative number, it's only when the number is negative that this happens, then you have to flip the symbol. So we have to try one where we're going to multiply both sides by a negative number. So I'm taking this one, x over -5 less than or equal to 2. What do? This is not a very big algebra. My x is not alone. We want it alone. My x is being divided by a -5, so I do the opposite, which is to multiply by -5. These cancel. My x's alone. 2 times -5 is -10. The symbol has to turn backwards because I multiplied both sides by a negative number, so it is now greater than or equal to. The or equal to doesn't change. The less than turned into a greater than. And we can test it. Let's test it. What's a number that's greater than or equal to -10? How about 25? That's way greater than -10. -10 is way over to the left of 0 on our number line. 25 is way over to the right. So this has to be valid. 25 is greater than or equal to -10. Let's plug it in. X over -5 less than or equal to 2. That's all the original question was. Plugging 25 in here. 25 over -5 is less than or equal to 2. 25 divided by -5 is equal to -5. Remember, a positive divided by a negative is a negative. And -5 is less than or equal to 2. So it worked. Plugging into our original question with a value that our final statement with the backwards symbol told us was part of the answer worked. That's interesting that we do this. It is something that is commonly forgotten by students who don't practice enough. When I teach my adult ed students, a lot of them don't remember this rule. And I always wondered why. Why don't they remember it? It's taught in algebra. Every math teacher who teaches algebra is going to cover this. So why don't the students remember it? And my answer is because in regular schools, frequently, algebra is an important unit in about 7th grade, 8th grade. It depends on where you're studying, which grade levels you encounter it. But it happens in more than one year because algebra is important. But they'll cover algebra for a few weeks. And then they have all these other topics that they cover, like geometry and the others. So what happens is by the end of the student will learn this rule when they're covering algebra. And maybe there's a test at the end of the week and they remember the rule and they apply it and they get the answers correct. But then by the end of the year, if they have a final exam, it's been months. They may have forgotten the rule. And what happens, of course, is that they don't realize that they lost a mark or two on the final exam because that little detail won't be worth very many marks on an exam. It's a small part of a big unit of algebra that's examined along with a lot of other units like geometry. So the student's grade and their course may be 1% lower or 2% lower. They don't notice. They don't realize that they lost marks because of that, because they forgot this rule. So that can happen. And that's why I like putting emphasis on this rule, because when you do move on to higher levels of math, this rule is not going away. It's part of algebra. And you will have some confusing wrong answers if you don't remember to apply it. But why does the rule work? I want to talk about that just a little bit, checking the time and checking how much stuff I still have left. Well, that's the end of the 3rd page. The but why comment is the last thing on this page, so I'll take away that page. And I want to briefly try to explain why I think this makes sense. Dividing or multiplying both sides of an inequality by a negative number means we have to turn the inequality symbol up backwards. So let's start with something we know is true, like 5 is less than 8. There's no x in this, but I can still do tricks of algebra with it because there is a less than sign, which is like an equal sign. So we can do stuff with this. But 5 is less than 8. On the number line, here's my 0. I'll put 5 here and I'll put 8 there. Yes, 5 is less than 8. We can see that. But what if I take 5 is less than 8 and I do one of these tricks? What if I divide both sides by negative 1? Well, 5 divided by negative 1 is -5. And 8 divided by negative 1 is -8. But if I just copied on this less than symbol, that's not going to be correct. -5 is not less than -8. -5 is greater than -8. So I have to turn the symbol backwards if I want it to make sense. Does this make it clear? To me, what I've said so far, it's not really clear. It's I'm on the right path. But what I think of is, if I take this 8 and I divide it by -1, the answer is -8, which is way over here. If I take the 5 and divide it by -1, the answer is -5, which is way over here. So what's happening is dividing both sides by a negative number, it's almost like it takes the number line and flips you right over to the other side. How about multiplying? 5 is less than 8. Same inequality statement, which we know is true. But if we multiply both sides by -1, 5 times -1 is -5. 8 times -1 is -8. I have to turn the symbol around for the same reason. Dividing or multiplying these two numbers by a negative number flips me over to the other side of the number line. And that, to me, is the best way of feeling confident that, yes, it makes sense to apply this rule. That's my explanation. That's my best explanation. I actually like it myself because I asked myself, well, do I feel more clear about this now after I explain it this way? And the answer is yes. It makes me feel more clear, like I understand it better, instead of just believing it, because I've always believed in this rule since I learned it when I first did algebra. I knew it was true, but why are we doing it? This little picture answers that question for me. And that little picture looks a little bit like a rainbow. Because, of course, there is a great overlap between math and art and the beauty of nature, isn't there? Okay, where's my clipboard? How much time do I have? Not very much. Okay, solve it both ways. You know how I like to do the same problem 2 different ways. So I'm going to show something. Remember, with a simple equality like this one, there's 2 things we can do. We can isolate our x, which happens to be on the right side, and we know that's fine. Or we could say, I don't like my x being on the right side. I can move it to the other side. And we're allowed to. And we did talk about this before. So doing it the way of a student who doesn't care which side the x lands on, it looks like this. I have to add 6 to both sides, because I want these to cancel. I end up with 16 equals 2x. I have to divide both sides by 2. These cancel. X equals 8. When I write my answer, I don't say 8 equals x. I just read it backwards. X equals 8, because I don't care if my x is on the right side or the left side of the equals. I know the answer is correct. But the student who doesn't like that and really likes the x to be on the left can do algebra and still get the right answer. That student is not going to move the 6, not going to deal with the 6 first. The student will move 2x. The student will say, I have a 2x on the right side and I don't want it there. That 2x is being added to the right side. I want to do the opposite. I want to subtract it. So I'm going to subtract 2x from both sides. Notice I'm going very quickly now because I know a lot of this is, well, all of this little discussion is a review. These cancel. But now I still have all this stuff with my x. I want to get rid of this 10. So I'm going to subtract a 10 from both sides. All that's left over here is -6. But I'll also subtract a 10 because I'm doing it over here. Now I have -2x equals -16. And we can see that this is working. My x is being multiplied by -2. I divide both sides by -2. These cancel. X is equal to +8, which is the same thing we had over here. So I can move all the numbers away from the x and isolate the x on the right, but I can choose to do algebra to the term that has the x and end up with the x on the left if I want. And I did this for a reason. Notice this is all equal signs. Now let's do one with an inequality symbol, which is the last thing I have time for. And I do not have very much time, so I cannot dawdle too much. Okay, let's get into this. How about this one? 8 minus x greater than 12. It's algebra with inequality. But we'll do it twice. 8 minus x greater than 12. It's a fast one. Okay. Normally, I would say, okay, well, this 8 is being added to the term that includes x. If you want to call that x, or that's being subtracted, or negative x, is up to you. But the 8 is being added. It's a +8. So I will subtract an 8 from both sides. These cancel. Negative x is greater than 12 minus 8, which is 4. Now I have to divide both sides by -1. I have to apply that rule. 4 divided by -1 is -4, but my greater than symbol has to turn into a less than. because we divided both sides by a negative number. How about, though, if instead of moving the 8 away from the x the way I did here, how about I move the x away from the 8? I do what that student who actually, if there's a student who actually likes the x to be on the right side of the inequality symbol, maybe that student likes that. So let's just say we want to do that. The x is being subtracted, so I have to add an x to both sides. These cancel. 8 greater than 12 plus x. But I now have to get the 12 away from the x. The 12 is positive, it's being added. So I am going to subtract 12 from both sides. These cancel. X is isolated. 8 minus 12 is negative 4. I never did that extra rule. I never divided or multiplied both sides by a negative number, so I never had to turn the symbol backwards. And yet it worked. Because if you read the answer, x less than negative 4, that's the same thing this says. X is less than negative 4. And yeah, when I'm reading it backwards, I have to do the symbol backwards. X is less than negative 4 is the same thing. Hey, that rule made me turn my symbol around here, but because I chose to do the algebra in my own with my own set of steps, and you can do that with algebra. Algebra gives you choices. I put myself in a position where I never had to apply the rule. And the reason I wanted to do this both ways is just to make you feel more comfortable with the rule. I'm not going to go out of my way to do this all the time to avoid having to follow that rule. If I were to do that, it means I'm very aware the rule exists. If I'm very aware the rule exists, why don't I just apply the rule when I need to? Really, it's okay to do it either way. And that is the last example, and I am getting to the end of my time. Very interesting topic. Algebra with inequalities and absolute value. And the fact that the two topics really are the same topic. You really have to know about both of them to understand each of them. And that was clumsily put, but I think that's an important concept. And being able to graph on the number line is extremely helpful to be able to understand any of these concepts. With that, I will say thank you very much for being here in Supercharged Math with Doug. Mocha, wherever she is upstairs, is saying goodbye for another week. I look forward to seeing you next week. Thank you for being so supercharged, and I will just stop talking and keep waving goodbye while I look at the chat in case there's any messages for me to read. Bye-bye.